Hello, everyone. I'm Rohan Basu, and today I'm here to present our work on characterizing and mitigating the I/O scalability challenges of serverless applications. This work characterizes and discusses the implications and the behavior of I/O in the serverless computing paradigm. Also, it recognizes several alarming trends in the serverless I/O, which can greatly impact the performance of different kinds of applications. To reduce the effect of such trends, this work also proposes simple I/O overhead and variability mitigation strategies. So with that, we start the discussion of this paper. So first, we give a little bit of introduction of serverless computing. So serverless is bringing in a new era of cloud computing. So from virtual machines, containers, we have moved to the era of serverless functions. The most attractive part of this serverless computing model is that the users no longer need to provision for resources. It is directly managed by the cloud providers and it scales up and down elastically depending upon the load. Thus, application program developers can now focus mainly on the code logic or the business logic and worry less about the deployment scenario. Also, serverless functions can spawn up in milliseconds, and typically they run for a few seconds or a few minutes. Each of these functions individually have small amounts of computing resources compared to traditional virtual machines in cloud computing. Hence, serverless computing paradigm is particularly helpful for applications running at high concurrency or small runtime applications or large applications which are broken down into microservices. This type of computing model is gradually becoming very common. One of the features of serverless functions is that they are stateless in their nature. So what this means is that these functions do not carry their state after they finish their execution. Hence, serverless functions fetch and write the output of the execution to a remote storage before they finish their complete execution. In this way, they perform the I/O. So this is a typical way of I/O in serverless, where functions read from a remote storage in the beginning of their execution and write back the output at the end of their execution to the same remote storage or to a different one. Due to this pipeline of serverless execution, the I/O component of serverless is becoming very important, and it has not been studied much by the previous researchers. The serverless I/O is network bound, and hence it can lead to several overheads and other challenges. Also, serverless vendors obfuscates the IP addresses of the serverless functions from the users, and hence serverless functions cannot really communicate among one another. Since serverless functions scale up to high concurrency, this obfuscation of IP addresses is done to avoid the excessive network overhead. This is a feature of serverless computing. However, frequently different functions need to communicate with one another, like individual components of microservices. Also, in distributed computing models, functions need to communicate among one another. Due to high concurrency and extreme parallelism of serverless function, these applications are very lucrative for serverless. Hence, in serverless computing, it is very common practice to make the functions communicate via an external storage. So every time a message is passed among functions, I/O is being performed. So these are the reasons why I/O in serverless is so important, and it is the basic means of communication among the serverless functions. However, most of the research in the area of serverless computing focuses on different other problems of serverless computing, like the cold start overheads, the scalability issues, and others. The I/O issues have not attracted much interest till now. But in this work, we find that I/O in serverless is significantly different from I/O in traditional VMs. And it has several alarming trends which can greatly impact the performance of serverless applications. This is the first work done which characterizes the serverless I/O over commercial serverless platforms and suggest mitigation strategies to avoid some problems in serverless IO. We hope that this work will help serverless program developers to better design and execute serverless applications, keeping in mind the issues related to the IO. So this work is done most in the most widely used serverless platform, which is the fast platform of Amazon Web Services called Amazon Lambdas. AWS Lambdas occupy more than 80% of the total serverless traffic at present. However, we confirm that the results and insights that are obtained in this paper are also valid for other serverless platforms like the Google Cloud Functions and the Microsoft Azure Functions. We study the performance of 3 widely used serverless applications, which cover a wide range of serverless computing scenarios. This includes a fully connected neural network, which we call FCNN. It performs image processing and image recognition by each of the serverless functions. Each request of this FCNN corresponds to spawning different serverless functions. The next application is a MapReduce sort application, in which multiple serverless functions jointly perform a single big sorting problem and writes back the output to the same file. The third one of the application is 1000 Island Scanner, or this, which performs video and audio processing. We have used AWS step functions as an interface to spawn multiple functions concurrently, which are spawned by the means of AWS Lambdas. We have tested the IO performance of 2 types of storage, AWS S3, which is a block-based storage, and it is a cheaper option for storage. And the next one is AWS EFS, which is a file system-based, network-based storage, and it is much costlier than S3. Currently, AWS Lambdas can access only these 2 types of storages. So first, we look into the median read performance of serverless functions. The figure on the left here shows the performance of spawning one function of each application. And as expected, we can see that the read IO is faster in EFS than S3. From the figure on the right, we can see that even when concurrency increases, EFS is the better choice than S3 for performing read IO. Of course, EFS is the costlier option. As concurrency increases for applications like FCNN, which performs IO on a large amount of data, the EFS throughput increases as the file system throughput scales up with their size. Hence, the median read performance decreases with the concurrency for FCNN. In this slide, we look into the tail read latency, that is the 95th percentile read IO latency at different levels of concurrency. We see that at high concurrency, the difference between EFS and S3 decreases. The choice of storage engine depends on the application. We see that for FCNN, S3 performs better than EFS. This is because FCNN reads large files and it causes contention on the network side of the network file system, or the NFS client of EFS. This causes a slowdown for some of the lambdas performing the IO. This is why tail read latency increases. Hence, S3 is a block-based storage. Since S3 is a block-based storage, each of the objects are treated separately in S3. And this kind of contention is not observed in S3. Now we look into the median write IO performance of the benchmarks. The IO trains become significantly different over here, especially at high concurrency. From the figure on the left, we see that the performance of write IO at the concurrency of 1. We see that EFS is no longer the clear winner in all the cases. In sort, S3 performs better than EFS because in sort, all the lambdas write to the same file. EFS maintains a strong consistency model and hence serializes the write to the same file, and this causes an increase in the total write time compared to the write time that we observe in S3. So S3 maintains an eventual consistency model, which is not that strict, and hence it does not suffer from this kind of issue. Now the figure on the right shows the write IO performance with an increase in concurrency. We see that as concurrency increases, EFS performs worse and worse compared to S3, and the write time gradually increases. This is due to two reasons: the right serialization of applications writing to the same file and the strong consistency checks of EFS. These two reasons limits the IO performance of EFS. For S3, there is no such consistency checks, and the consistency checks in S3 are much more infrequent than they occur in EFS, and hence the write performance remains almost constant as the concurrency increases. Here in this slide, we see the tail write performance. The tail write time gets worse with EFS as the concurrency increases, but remains almost constant with S3. Along with the consistency checks, EFS is also throughput bound, unlike S3, where throughput depends on the bandwidth of the individual serverless Lambda functions. This limits the capability of EFS when it performs IO, especially at high concurrency, because at high concurrency, the contention of write IO is much more. Serverless applications that rely on concurrent invocations to synchronize at the end of the write phase, for example, applications like sort, they can suffer greatly in EFS due to this kind of contention, especially at high concurrency. The consistency checks provide high security and availability for EFS, but they might hamper the serverless IO write performance. So we saw that EFS write performance deteriorates a lot at high concurrency. EFS is the costlier option than S3. However, even still, a lot of applications still might prefer EFS as a suitable storage medium due to its file system structure, which is suitable for various kind of programming models, unlike the block-based storage structure of S3. Also, EFS provides higher level of data security through its strong redundancy checks. These are the reasons why EFS might still be the favorable storage medium for certain applications. So unlike S3, EFS also provides a stable throughput level, which depends on the size of the EFS. A common way of improving the performance of this kind of elastic file system is increasing the throughput of the EFS, which will result in higher bandwidth for the serverless functions. Throughput can be improved in two ways. One way of improving it is increasing the capacity of the EFS, and the other way of improving it is provisioning higher EFS throughput by paying extra dollars. But unlike the traditional beliefs, neither of these two approaches consistently improves the performance of EFS. Even sometimes the performance can become worse. In the previous slide, we saw the read IO performance on increasing the throughput capacity and storage capacity of EFS. Here we see that even the write performance follows similar trends. With higher throughput of EFS, still there is no guarantee that the write IO performance will improve. This is because of the fact that with an increased EFS bandwidth, the NFS servers behind the EFS get overly congested. Hence, request of accessing the EFS through NFS clients gets dropped, and later when the congestion decreases, the requests are reissued. The whole process increases the write IO time, and this causes degradation, especially which is noticeable at a high concurrency. So EFS can be a suitable choice of storage medium for applications as it allows a stable throughput level, unlike S3, and also due to its file system structure. But we saw that the write IO performance issues related to it, and it can't be mitigated through intuitive techniques like increasing the throughput level of the applications. Now the question is why the write IO degrades at high concurrency. This is because at high concurrency, there is high contention as all the different serverless lambdas perform their IO together. Hence, one way to mitigate the write IO performance issues of EFS is to misalign the write phases of the concurrent serverless function so that they are less overlapped. This can be achieved by staggering the lambda invocations with What that means is that the lambdas are divided into batches, and each of the batches is spawned with a little bit of delay in between them. Thus, the batch size and the delay are the two variable parameters in the staggering process. With staggering, the lambdas perform concurrent IO. Lambdas performing the concurrent IO decreases, and it decreases the overall contention. Now, here we'll see the performance of IO with this staggering approach. And in this slide, we show the performance of serverless IO with different batch sizes and delay due to this staggering. We can see that indeed the read and write time decreases, causing an improvement in the read and write IO performance due to the staggering. This improvement can be observed when we appropriately choose the value of the parameters, that is the delay and the batch size. These parameters are application dependent. We note that even though the read performance of EFS was originally better than S3, it still further improves the read performance of EFS due to this staggering approach. However, one thing to note over here is that improving only the read and write performance is not the main goal in this staggering approach. This is because staggering introduces a new delay during the spawning of these batches. These delays accumulate till the spawning of the last batch, and the summation of these delays is called the wait time. So this wait time combined with the IO time and compute time of serverless functions results in the service time. If we can show that due to the staggering approach, the service time decreases, then only we can prove that this approach is useful. From the figure on the top, we can see that indeed staggering increases the wait time to spawn the lambda functions. But from the figure on the bottom, we can see that staggering still decreases the total service time of applications due to an overall decrease in the write and read IO time. Due to staggering and following this kind of staggering approach, the write and read IO performance both improves, and the IO performance can be improved by a total of almost 85% if the delay and batch sizes are chosen appropriately. That's it for most part of the paper. This is the first work done which characterizes the IO performance of serverless applications. It discovers several non-intuitive IO trends and practices that are not readily available from the other researchers. All the data and serverless spawning scripts used in this paper are publicly available, and you can access them from the given barcode. Please refer to our paper for more interesting trends related to the performance of IO from traditional EC2 virtual machines, how serverless IO is different from IO in virtual machines, and what are the results of micro-benchmarking these serverless platforms. Also, we show the effect of random IO in serverless platforms. Thank you for your attention.